Today we're going to talk about capacitors. Now capacitors are parallel plates that store charge. Now when we think of parallel plates, think of two rectangles that are parallel to each other, so they're not touching but they are close. And these are attached to a battery, which we draw like this. Looking at that in 3D, we can draw it like this. So these are two parallel rectangular prism like boxes that are long and rectangle. These rectangular boxes, which we call capacitors, store charge. So this is a battery, and we're going to say that this is a 9-volt battery, which means that from here to here there's a 9-volt rise. We talked about voltage in the last section. So, for capacitors, we have a unit to describe what a capacitor is, and we call that capacitance. And we get that units of C. And we call this, the units for it are farads, which is F. And a farad is equal to a coulomb over a volt. So, a key equation we need to talk about is this. Charge is equal to capacitance, which is in farads, times voltage. So let's say that these capacitors are 6 farad capacitors. And these are 9-volt batteries. So we can figure out the charge that is stored on each plate. So charge is equal to capacitance, which is 6 farads, times voltage. This point is 9 volts higher than this point, so 9 volts. And we know from right here that the units for farads are coulombs per volts. So the volts in the denominator cancels out with the volt in the numerator. So we get 54 coulombs is the charge in each plate. Now what does that mean? This means that on this plate we have a charge of 54 coulombs, which is the charge. And on this plate we have a charge of negative 54 coulombs, because we know that when a positive charge is created, an equal negative charge is also created. And the positive coulombs attracts with the negative coulombs. And the same is true for these 2 points right here. This system is this system, but in 3D. So remember this equation. Charge equals capacitance times voltage. So, we're going to go over parallel plate capacitors. So we have these two plates. One is of positive charge, like in this example, and the other is of negative charge. And they're attached to something. So we're going to have electric fields going from the positive charge to the negative charge, like we talked about in previous sections. We have a certain distance between the two plates, and each plate has a certain area. in 3D, one of the plates looks like this, and this is the area right here. Knowing all these things, we can figure out what the capacitance of the system is going to be. Capacitance is equal to sigma R, which is the dielectric constant, we'll talk about that in a little while, times sigma naught. We know sigma naught to be equal to 8.85 times 10 to the negative 12 coulombs squared over newtons per meter squared times area over distance. In the book I'm using, the dielectric constant, which I called sigma R, is often called K. I don't like calling the dielectric constant K because in previous sections we've said that K is equal to 9 times 10 to the 9. This is a different K than the dielectric constant. We're not using that right here, which is why I'm saying that the dielectric constant is this. So, if given all these parameters, if given area and distance, you know these two are constants, and you can solve for capacitance. To solve for the dielectric constant is dependent on what's inside the capacitor. In this example, we're assuming that inside the capacitor is air or a vacuum, and that means that sigma R, which is the dielectric constant, is equal to 1. We can use different materials inside the capacitor which changes sigma R. When doing a problem, they're going to tell you, is it a vacuum or air? Then you assume it's 1. If it's not a vacuum or air, which they'll tell you, then they will also give you the dielectric constant, which you will use to solve for capacitance.